Hello my friends, now I will use the transistor, this NPN bipolar transistor. Click, okay. Drag the workspace, very nice. Now go back to resistors, 5 resistors, click, okay, 5 resistors, and place the resistors just like this. And 3 polarized capacitors, 1, 2, and 3. Okay. This rotate, okay, just like this, rotate. Rotate this here, okay. Okay, and be careful with the polarization of the capacitors. Look at the plus sign here. The polarization, be careful. Join the nodes. Okay, add more grounds. 1, 2, 3. Very good. Now add the voltage source that will be the power supply. Join the nodes. And finally add the AC alternating current source. Alternating current source. Okay, very good. Now modify the values of the resistors. And adjust 4 kilo ohms. Up here 7 kilo ohms. This another 1.5 kilo ohms, 1.5 kilo ohms. Up here only 220 ohms. not kilo ohms, only ohms, 220 ohms. This resistor, 1 kilo ohm, okay, do not modify this and modify the values of the polarized capacitors. By default is 1 microfarad and adjust to 47 microfarads. Modify the 3 capacitors. And this adjust 47. Okay. Now modify the power supply to adjust to 10 volts. 10 volts. And modify the alternating current source. The signal that will be amplified, go to adjust and use sine waveform, DC voltage 0, amplitude only, modify amplitude to 100 millivolts. 100 millivolts. Frequency change to 500 hertz. 500 hertz. Phase 0. Okay. And verify the here on adjust the transistors, the NPN transistor settings. Okay, verify the saturation current 1 femtoampere. Beta is 100 ampere, okay, 100. Reverse beta 1. Collector resistance 1 ohm. Base resistance 1 ohm. Emitter resistance 1 ohm. Okay, very good. And run time domain simulation. Okay, not run frequency domain simulation, not. I will do it later. Run time domain simulation. Okay. Okay, very good. Okay, and pause, rewind. Okay, I want to know the value of the current in the emitter of the transistor, in collector, and in the base. So I will disconnect this node, delete. Okay, and this circuit will be connected only to direct current voltage. Okay, only to DC voltage. Run time domain simulation. And now you can see the current on collector is 1.88 milliamperes. On emitter 1 milliamperes. Okay, and on the base I don't know the current in the base, so I will add this ampere meter. Okay, ampere meter, and also I want to know the voltage, uh, and I want to know the voltage, and also I want to know the voltage between the collector and emitter. And when you run time domain simulation, also I don't know what is the voltage between collector and emitter. Okay, pause, rewind. Also add a voltmeter. Okay, so do some space and make some space. I will remove these nodes, these connections, delete, and add the ampere meter, rotate. Okay, I need more space. Okay, add the ampere meter and voltmeter. Okay, more space for voltmeter. Okay, add the voltmeter. Okay, more space. Enjoying these notes, very good. Okay, very good. Okay, disconnect the alternating current source. Okay. Okay, and run time domain simulation. Okay, and I will take notes. Okay, the current in the base is this value, 18.8 microamperes. Okay, and collector current in the collector 1.88 milliamperes. And the current in the emitter is 1.9 milliamperes. Okay. And also the voltage between collector and emitter is 6.73 volts. Okay, very good. And why you get these values? It's very simple. The current in the collector is equal to beta times the current in the base. So current in the collector, select the transistor and adjust forward beta 100. 100 times the current in the base is this. Is 18.8 microamperes. So the result is 18.8 micro is minus 6. Okay, this value times 100 is this value 0.00118. So this is 0.00118 and all, and you know is the same like this. Okay, very nice. Also, you can demonstrate or allow the current in the emitter. Current in emitter is the current in the base plus current in collector. And this is current in the base plus current in collector. Okay, and this is equal to, okay, current in the base 18.8 minus 6 plus 1.88 minus 3 equal is this. And this is equal to this. Okay, very good. Very good, my friends. Okay, and now, so this is the polarization of the circuit. Okay, the polarization of the transistor. Verify with this, and all is very good. And now pause, rewind, connect the alternating current source, run time domain simulation. Okay, very good, and pause, rewind. This is the input of the amplifier, and this is the output. So I want to see the waveforms. Okay, click here and show waveform in the input. Click here, show waveform in the output, and runtime domain simulation. Okay, very good. But modify the simulation speed. Modify to 1 milliseconds per second. Okay, you know real time is 1000 milliseconds per second. I'm using 1 milliseconds per second. Very nice. Click on workspace. The the wave the wave in blue is the input. The wave in green is the output. Okay, the input is a sine wave. Okay, sine wave, but the output is not very good. Okay, but the output does not look like a sine wave. Okay, my friend, it is true that the input is amplified by the circuit. So the question is why the output is not a sine wave. Okay, the circuit is amplifying the signal. Okay, the output has more amplitude of the input. Okay, maximum value of the input 100 millivolts. The output has a maximum value of 344 millivolts. Okay, amplified by Liu. The frequency is the same, 500 hertz. Okay, but this is not a good amplification, my friends. I want to know why. Okay, and so to fix this, you can modify this resistor. For now, the value is 7 kilo ohms, but adjust, I will modify lower value. Okay, before to do that, verify the input maximum value 100 millivolts, minimum minus 100 millivolts, frequency 500 hertz. But the output, the maximum value is 344 millivolts, and minimum value minus about minus 1 volt. So the output does not look like a sine wave. Okay, so I will use this resistor and modify the value to change from 7 kilo ohms, a lower value like 1 kilo ohm, and wait a minute, 1 kilo ohm, and review the parameters. The output, the maximum value is higher than the previous value, 649 millivolts, minimum value about minus 2 volts. Okay, so this is much better, but you can modify the resistor again, for example to 220 ohms, and wait a minute. Okay, and this is much better, like the output maximum value 860 millivolts, and minimum value minus 550 millivolts. This is more symmetrical. Okay, okay, this is much better. Click on workspace. Now you can see the input and output. The phase is not equal. Okay, also the output is not a perfect sine wave. Okay, but this is much better than the previous result. Okay, okay, but click on the resistor and modify. I will use finally 300. I will use finally 330 ohms. Okay, click on workspace, pause, rewind, and run time domain simulation again. And wait a minute. Okay, review the values. Okay, and the maximum value of the output is 873 millivolts, and the minimum value minus 763 millivolts. Okay, more symmetrical wave. Okay, now you can see 800 millivolts and minus 800 millivolts. This is very good. Symmetrical wave. Okay, and after this, pause, rewind, and run frequency domain simulation. Run frequency domain simulation. And now you will see this for 500 Hertz. Okay, the phase difference is minus 128 degrees. Okay, this is the phase difference. Okay, the phase difference between the input and output, and the gain of the input is minus 20 decibels, and the output 6 decibels. Okay, this is the gain. Okay, for 500 hertz. Okay, and rewind and modify this. You can modify the frequency. Adjust. Now is 500 hertz. I will use amplitude 100 millivolts, frequency 1 kilohertz, sine wave. Okay, click on workspace and run time domain simulation. Wait a minute. Okay, very good. Look at the output, about 800 millivolts, minus 800 millivolts, frequency 1 kilohertz, very good. And pause, rewind, and run frequency domain simulation. And now the frequency is 1 kilohertz. The output with the gain of 8.65 decibels, more than the previous gain using 500 hertz. And the phase is different, minus 148 degrees. Click here on the input, is this graphic, but click here on the output on this green node. Now you will see the graphic. One kilohertz. Okay, look at the green line, the green curve. Okay, so this is a high pass filter, more frequency, more gain. And if you see the light green curve down here is the phase difference. The phase difference. Okay, I'm using 1 kilohertz. Up here the gain is 8 decibels, but the phase is minus 148. Okay, on the left the gain in decibels, on the right the phase. Okay, but the gain, for example here for example here for 30 hertz the gain is about minus 17 decibels. The phase difference, the phase is about minus 70 degrees. Okay, this circuit is very good. This amplifier is very good for frequencies equal or higher than 1 kilohertz. Okay, but for example on 5 kilohertz you will get a gain of 10 decibels and a phase of minus 180. Okay, click on workspace, rewind. Also you can click here and change the sine wave, adjust. You can use square, low 0, high only 100 millivolts. Okay, low 0, high 100 millivolts. Period 1 millisecond is the inverse of 1 kilohertz frequency. This is very good for 1 kilohertz frequency. 1 millisecond and width 50, rise 0, fall 0, delay 0. Okay, use these values for the square wave and run time domain simulation. Okay, wait a minute. And the input maximum value 100 millivolts, minimum value 0, frequency 1 kilohertz. But the maximum value of the output is 800 millivolts, minimum value 700 millivolts, frequency 1 kilohertz, and the phase looks like a difference of 180 degrees. Okay, it looks like an inverted wave. Okay, pause, rewind. Thank you very much, my friends.